Assalamu alaikum. Good afternoon, everyone. My name is Abdullah Hyab Al-Kitwi. I am the chairman of the operations board at Adia Lab, and I would like to welcome everyone today to Adia Lab seminar series. It is my pleasure to introduce our esteemed speaker for today's seminar, Dr. Vepakomma. Dr. Vepakomma recently completed his PhD at MIT. Congratulations. And he has since joined the Department of Machine Learning at Mohammed bin Zayed University of Artificial Intelligence in Abu Dhabi as an assistant professor. His extensive industrial experience includes significant roles at Meta, Apple, Amazon Web Services, Motorola Solutions, Corning, and several innovative startups. Dr. Vepakomma's impressive academic journey includes a master's in science and mathematics and applied statistics from Rutgers University. His research expertise lies in developing cutting-edge algorithms for distributed computation in statistics and machine learning, with a particular focus on privacy and efficiency constraints. His outstanding contributions to the field have earned him numerous accolades, including Meta PhD research fellowships in applied statistics and the 2 SERC scholarships from MIT Schwarzman College of Computing. In addition to his academic and professional achievements, Dr. Vepakomma is the co-founder of Integrity Distributed, a research-based nonprofit organization that was honored with the Financial Times Digital Innovation Award. Today's seminar will explore the fascinating realm of distributed and private computation, addressing the challenges of data centralization in the face of stringent privacy regulations, computational and communication constraints, trade secrets, trust issues, and competition. Dr. Vepakomma will shed light on the innovative method that enables seamless collaboration and data-driven prosperity, with applications ranging from digital health to finance. Without any further ado, please, Dr. Vepakomma, please, the floor is yours.
Thank you so much for the very kind introduction, and very happy for all the coordination and the organization that went into this effort. Let me switch into this. So. Is this synced in? Is that? All right, great. So all the logistics are done. All right, thank you. Welcome to the talk. So this is my talk on breaking silos. So this is about data silos. We don't want to break anything else. We definitely want to build bridges. Again, bridges between organizations that hold data silos or entities that hold data silos. And what is these constraints that is causing this problem to exist in the first place? So the constraints of privacy and other trust and regulatory constraints that you would see more about. Okay, so let's keep going. All right, so there's been a lot of buzz for a while on the big data era, and the big data era was rightly, it was definitely a revolution that started after the ICT revolution that happened in the communication era. So, but there's an invisible data problem that we literally are living in right now. We're always surrounded by an invisible data problem in the big data era. So that causes a small data problem because you have a lot of big data, but they're siloed away. You could get in a lot more out of the bang for the buck if you can solve this problem. Okay, so what do I mean by data silos? This is a bit abstract and cartoonish diagram. You will see more real life use cases or like a case study as we keep going forward. So by a data silo, I mean, there's a lot of devices around us and that are holding data. So I would call them the data providers. And they're holding invisible data. Why is it invisible? Because they need to interact with other providers that help them enable service. to get some utility out of your data. So the other provider could be doing some sort of additional processing, or could be a contributor of data itself in addition to processing. And there's a disconnect between these data silos that's caused the invisible data. And the disconnect, as I said, is caused computationally due to resource efficiency constraints like compute and bandwidth as the GPUs are getting, the servers are getting stronger and stronger. These are more computational constraints, but also there's like real life societal constraints that are being regulated in different ways across the world. So that's the privacy constraints. So how do we solve this problem, right? Let's think of a case study. So this is not the most fanciest case study, but it's very real. That's the reason I chose it. It's a very real case study. There's a lot of websites that people use for different kinds of services because we're living in the internet world. But there's a cookie apocalypse. That's a slang term that's being used to refer to this problem. As different kind of regulations on data protection and privacy started kicking in, this has been an evolution of the regulations. There's not a list of all the regulations, for example, GDPR and the CCPA, and there's many more that you'll see and hear about. There's been some sort of a gaming of trying to be compliant to the regulation while still being able to access more utility from the data. So the compliance kind of game has been going on for a while, but this has led to cookies being disabled, or going towards a world where cookies would be disabled. And what are cookies, basically? Just to get a feel for this problem. Whenever you visit a website, there's a first-party cookie that locks some meta information about the website and your relationship with the website. So far, first-party cookies are not as much of a problem in general. Those are just enabling you to use the website in the first place. The website has components that are dynamically coming in and building and offering you additional services. And advertising, of course, is one of these components. These keep changing based on what website you are and based on all the meta information you're providing. And that's the advertising piece that is, and the data that comes with these third-party cookies coming from different dynamic parts of your website, which is driving the advertising economy, which is a huge economy, as you can guess, the digital advertising economy. But as regulations started kicking in for ethical and also legal reasons, companies started changing the way they log information out of these third-party cookies. So companies started blocking third-party cookies, and Google kind of announced that they would eliminate third-party cookies from the entire ecosystem. And they've been saying that they'll do it by 2023. They've been kind of postponed just to be able to figure out how the entire ad ecosystem and all the other companies would kind of react to this and kind of give them some time. So that's a very real problem that is happening all around us. This is one invisible data problem that would be faced by these large companies. But the world is not always about large companies, right? So, the big takeaway I wanted to give you from that case study, so this is more like a case slide, right? It's not even a case study, but it's like overall takeaway is regulations have happened very locally from a geographic perspective in the EU. But they're impacting globally. The repercussions are happening globally because these companies are multinational. We're living in a world of globalization where the companies are operating with a customer base that is geographically held. So there's local repercussions and changes to the regulatory space that are kind of causing global issues. There's been an adage for a while about think globally, act locally. This was from a global perspective. Think globally, get takeaways, and improve locally in the economy that you are coming from. Now in the privacy space, that's a bit different now. The learning is operate and comply globally. So comply. Continue to act locally in a way that is beneficial to your ecosystem. And this is a real thing. So as you see, I put in UAE in there, there's a data protection law. All of these laws are evolving. There's the CCPA and HIPAA in the US about credit card data, the Cloud Act, and then the HIPAA for the healthcare, and there's GDPR. That's been introduced in the EU, and so on and so forth. And there are many companies that interact with customers all over the globe, so they need to act and comply globally. And what does it mean to comply and act globally while still acting locally? And there's just a listing of some more of the regulations, just so that you get a feel for some of the things that you saw on the map. There's the GDPR, there's HIPAA about healthcare, there's Cloud about Overseas Use of Data Act. There's an act about, for example, of a company that is, say, held in the US that has customers all over the world, because we're talking about global operations. And it's an act about what it means for the lawful overseas use of data. So if they take data from the US and they're using it overseas, what does it mean? How do you keep a track of that? Are you using it for the right purpose or the wrong purpose? And the other way around. Okay, so that's the learning number 2 that we're getting to from the case study, which is one needs to have a better mapping between privacy enhancing technologies and regulations in the space. How do you know that you're compliant? Because you know that compliance is important, but how do you get to that? How do you enable the seamless collaboration? For example, there's been some work done around this. So there's an area or like algorithmic area of work called k-anonymity that was very popular. It's some sort of a structured way of anonymizing your data, making sure that it will preserve some privacy. And most companies do some level of anonymization anyway. Since the GDPR thing happened, there's been a clause in the GDPR law on identifiability. They want to prevent identifiability of a specific person when there is some data sharing or like data-enabled service that's happening. And it's been kind of mathematically proven in this paper that k-anonymity does not satisfy this clause. We want to have this kind of a mapping because there's a lot of technologies that you can put in the privacy enhancing tech space, and there's a lot of evolving regulation. No one really knows what is the right way to operate and what kind of method satisfies which clause. That's a real problem that we need to solve in the current day so that it's going to have some benefit in the future. Learning number 3. One needs to have some sort of provable guarantees against the worst case. In terms of machine learning and AI, generally, the performance that you care about is on the average case. On average, you want to do better on your test data. You want to train a model on some data, deploy it, and do well on average. And that's what the machine learning models of this day and age are trying to minimize, which is great, which is good enough. I wouldn't recommend you need to change that unless there's a specific case for not operating in the average case. But on the privacy side of things, you need to be able to have provable guarantees on the worst case, because privacy is a worst case. It's kind of a constraint that you're attacking. So you need to be able to have a privacy guarantee in the worst case, which means even a single individual's identifiability should not be leaked, and so on and so forth. Or like a group of individuals' identifiability should not be leaked when you're building data-enabled services. At the same time, there's been a lot of mix-up of technical and generally used terminologies. For example, obscurity is not security, right? If I come up with some way of shuffling things up and try to obscure what I'm saying, that doesn't mean security, right? There's been an adage for a while. At the same time, if I do something heuristically, which is some sort of a guess, where I don't have any guarantee of privacy, but I have some sort of a guess and I show some empirical results saying this reduces some leakage about your data. That is not enough. That's good. I mean, maybe it's a good building point for something else, but that is not enough. And also there's this misuse and like shuffling of swapping of words of privacy and security. Privacy in the technology space means something very different than what security means in the technology space. So just to clarify, privacy means you need to be able to have a privacy about your sensitive raw data when you share the outputs of some processing. So it's a guarantee on the outputs. So if I compute some statistics and release it, or if I build a machine learning model and share the weights, all of these are outputs. And based on outputs, I need to fuzz something so that I provide guarantees on the inputs, which is your sensitive records. In the same time, what is security? Security is more about the same thing, again, protecting your sensitive data, but the protection is not on the outputs. The protection is on during the computational pipeline. Maybe you encrypt your data into a lot of hashes and you do some sort of computation and you get the right answer. So that's the security. So there's a general meaning for societal meaning or like a linguistic meaning for privacy and security. I'm not arguing against that. But on the technical side, these are very different things. Both are important. They're different. That needs to be identified. Okay, so this is a bit of a very broad stroke of where we were and where we are heading towards within the context of this talk, right? Back in the day, this is the black and white figure. Maybe some of you might be able to guess what's happening there. That's a telephone exchange that is manually operated. So when you try to make a call, you book a call. They call it some sort of a trunk call. There were different variations of it. You call the exchange. There are people literally working in there. They take your number and then the number you want to call, and then they do some switching of wires so that you're connected to the number you're asking for. This is how telephone exchange really operated. since the invention of the telephone in the early days. Now that kind of looks funny to us, and it's kind of unbelievable that it was that bad. But of course, that was a great development back in the day. They were enabling communication. A few decades down the lane, that's not what's happening. There's seamless communication. There's the whole ICT revolution that happened, and we take it for granted, right? So what we're going through right now is a similar problem, kind of a funnier problem. There's a big data being collected everywhere, but they're being siloed in the most cases. Most data is siloed on my phone, across organizations, across countries. And for the right reason, they're siloed, because privacy and security is also important. I'm not saying everyone needs to share everything with everybody. But there's a problem that we're going through, and not everyone sees it, but it's all around us. If you think through that lens, you'll see it everywhere. And where's the future that we want to head towards? We want to have the similar kind of seamless communication that we take for granted, because now we have smart models and smart AI coming up. We want to get towards seamless collaboration, because you don't want these smart models to be sitting on individual data silos. You want to get to seamless collaboration, and privacy needs to be taken for guaranteed in your pipelines by default. Whatever thing happens, that should be secure and private. That's the future we want to be heading towards. And talking of collaboration, there are many forms of collaboration, because there's two aspects. Privacy is a constraint that you are trying to remove in order to enable some sort of collaboration. Collaboration is where you gain utility from. There are different kinds of collaborations, even in today's world. Like there's a centralized version where you have a bunch of client devices. You could have millions of cell phones. There's a server in a company. You could have a few silos that are operating with a server. Maybe these silos are healthcare providers that are operating with another insurance provider who has a server. There's decentralized or peer-to-peer kind of collaboration, and so on and so forth. There's a vertically partitioned collaboration, which is very popular in the financial sector, actually, where you have different companies collecting different things or different variables or different features about their customer. So maybe there's a company collecting about their information about their banking behavior. There's another company collecting information about their credit behavior, and so on and so forth. Some other company collecting their geolocation data based on where they're going, what they're doing. So that's called vertically partitioned, so on and so forth. And what is the tenets of like a good collaboration enhancing tech? Because you use a privacy enhancing tech to achieve collaboration, but then what's a good collaborative enhancing tech? Of course, privacy is one of those things. I'm not saying there's everything. Privacy and one needs to be compliant, the tech needs to be compliant so that collaboration happens. Resource efficiency is a huge thing, especially on the computing side of things. You want to care about compute and communication bandwidth or efficiency, right? Because you can't think of a world where you can train an LLM yet, or like a large language model or a GPT on your cell phone completely. Of course, there are some hacks around how you fine tune and so forth on a cell phone. Maybe we'll get there. I would bet that maybe we'll get there because there's a lot of unexplored inefficiencies that's not been extracted yet. But at the same time, there's a communication bandwidth issue, so that's a resource efficiency. There's a self-organization behavior, because you can't assume that you would have a collaboration between all the billions of people that live in this world in some form or the other. They would form cliques and organize into different sub-cliques of collaborations in a natural way, and the ecosystem would evolve. If you have the right technique, you would see platforms that are small and big that will enable self-organizing behavior across the world. There needs to be incentivization, because there needs to be some money flowing in and out of the system. Otherwise, how would it work, right? So how do you see this as a product, as a digital product, right? If there's a collaborative way to, say, learn a machine learning model, all the entities that are contributing their data, that's the raw material that they're contributing. And that could be privacy sensitive data. So you need to give them guarantees that your data would not be misused and is being taken in a privacy preserving way. And they're contributing this raw material. And there's a server or like some entity or an orchestrator of any form of this collaboration that is building the final product. That is your model. So you're going from raw material of data to a final product. The product wouldn't have been very good if the collaboration was not possible, because you then build data just based on one silo of data, not all silos of data. And when this happens, there's give and take of raw materials and products, and the product is being downloaded again, the model, and this thing continues for a while. There needs to be an incentivization of this behavior. Otherwise, how would someone go after every single person trying to get data in the right way? So that would create room for markets, digital data markets and model markets. We know about markets like Amazon, which is like tangible goods, but it would be a real thing eventually where you'd have, that's my bet again, where you'd have markets for digital goods that are specific to AI or machine learning or data science broadly. There's data markets and model markets that would come into play. that would create supply chains and an ecosystem for AI supply chains. And there also needs to be someone to bell the cats, which is a compliance tech is going to stay. The regulations are getting tighter and tighter, and they're getting mapped closer to technologies day by day. So there needs to be compliance tech to be able to do auditing and checking for all sorts of attacks and privacy defenses. Okay, so this is the kind of work my research broadly focuses on, right? So it's trying to connect silos, and the hope is to unlock some value, right? And how does this realistically happen when someone looks at this kind of problem? There's been a lot of foundational good work that's been happening and has happened in the ML, statistics, and broadly scientific computing space. It's a very important building block. It's been very foundational. What would sit on top of that is you need to take different queries or different processing that you'd need to do in any of these areas foundationally and be able to move it to the distributed and private regime. How would you do that in a distributed and private way? At that point, you can also need to be thinking about applications to healthcare, finance, and so on and so forth. So that's how one would unlock value through those areas. Okay, so let's do a quick walkthrough of one technology in ML called federated learning that enables to do collaborative machine learning. Right? So it's a collaborative method. It's not necessarily a privacy enhancing method, but this method can work well with privacy enhancing tech. Then you have like private federated learning. But what is a collaborative learning that you could do with federated learning? You might have heard about this. There's many devices all around us and many entities. That's in the bottom row. They have their own sensitive data. They can train models using their own computational resources, and they have different kinds of models that they train to do their own AI tasks. And those models are shared with a server. So there's a centralized form of collaboration based on one of the previous slides you saw. You're never sharing raw data. You're sharing models, which is good. At least you're not sharing raw data. I'm not saying it's private. It's good. It's a good start. And then the server is averaging these models or doing some sort of a weighted ensemble of these models so that an improved model is learned from all the individual models. That's one form of centralized collaboration. The improved model can then be downloaded by all the clients. Okay. This is great, but if you think about a server, typically servers are powerful. Servers can do a lot of work. These are huge companies. All they're doing is an average operation, something that we've been doing on Excel sheets all the time. I'm not saying doing an average operation at this scale is very easy, but still it's not the hardest problem. The harder problem relatively is training a model, which in this setting, the client is supposed to do. The client is supposed to do most of the work of training a model while the server is just doing an average operation. Something seems a little flipped up, which could still be improved, right? So it's a great start. So another line of work that's a very interfering learning that solves this problem is called split learning. What this does is follows. This is some work that we introduced. In this setting, you have the same problem, the same entities holding sensitive data, but instead of training the entire model on the client, you're splitting the model. So you're doing some sort of parallelism, right? You're doing model and data parallelism. There is data anyway that's parallel, but you're doing model parallelism. The task of training the model, that work is being shared by the client and the server this time. So you're doing some sort of data parallelism. There's not the most amount of parallelism you could do because ideally you should be able to parallelize every single operation that the client is doing and offload across different cores or servers and so on and so forth. Well, there's one level of parallelism that you're adding. In this setting, the client does lesser work, server does some work, which is better. At the same time, the client can tune how less or more work it can do based on its resources. That's also good. The amount of communication bandwidth that goes out in federated learning was the entire model. This could be like gigabytes or terabytes if it was like a very large model. But in here, it's just like one layer of intermediate transformations of your data or the activations, which is a very, very tiny payload to communicate over the bandwidth. You don't need a huge data plan to do that. This is very easy. Relative to federated learning. So we've improved some resource efficiency in the collaborative learning setting over federated learning in this form. And there are many variants of this that we published. Now thinking about the collaborative technologies that we saw, some of these things, this is great. This causing more resource efficiency and adding some benefit. But at the same time, there's still the privacy, the elephant in the room, the privacy. Because these model weights that you're sharing, any communication that's happening in collaborative learning, in FL or in SL, federated learning or split learning, is not proven to be private. There's actually been many number of attacks that have been shown that you can kind of reconstruct most of your data of most of your raw model from the ensemble model at the server. And this is a server that you don't necessarily believe in. Having trust in someone is not guaranteed. There's no verification of trust when you send these models to the server. So FL is a great solution, or like SL is a great solution for collaborative aspect of the learning. But then there's still the elephant in the room, the privacy aspects. So when it comes to different fixes for the privacy aspect of, say, adding privacy to a machine learning model, there's a lot of work that has happened there too. There's been methods. So there's a broad categorization of these methods. There's been methods that kind of fuzz the raw training data itself, the raw sensitive data, and then do the learning of the model. And they try to fuzz the raw data in such a way that you get some sort of utility while having privacy guarantees. That's how the fuzzing is learned. But this is too bad, because in today's large machine learning models, you have millions and billions of multiplication operations. So when you add very little noise, and then when you start multiplying millions and billions of times as you keep doing the neural network operations, your noise is going to blow up so much, because any noise variance blows up by a square. So if you add some noise and do some operation, it blows up by a square, even if you just scale it by a single constant. Now, if you're doing billions of operations, all that would come out if you add noise there is just almost white noise, something that has no utility. It's private, but it's not useful. But then there's no value in that either. That will not unlock collaboration. So there's been improvements to that, where they try to perturb the learning of the model. When you're learning this model, you're learning different gradients of this model. You try to perturb the gradients in a nicely calibrated way so that you get better accuracy. This has been the most powerful and most impactful that's been able to squeeze the most utility for training private neural networks that fall in the class of methods that are to do with gradient perturbation. And of course, there's a lot of variations. The early method was called DP-SGD, where SGD is a standard optimizer, SGD atom for training neural networks. They did a differentially private version of it. It's a privacy guarantee on training neural networks. They had about like a 20% drop in the accuracy of these neural networks between the non-private and private versions. That's not good, because right now we're in a world where people are fighting for like a 1% drop in accuracy or a gain in accuracy, because that translates into a lot of impact if it's an important problem. So 20% is not good. It's private, but then you're losing utility. And then there's been a lot of work where they came up with the most recent advance there in that space has been called DP-FTRL, follow the regularized leader. DP is differential privacy. There, Google has actually a very scaled up deployment where they're guaranteeing a very high privacy level for the entire Latin America region, the LATAM region, which is still, again, millions of customers for, say, like their Gboard application, which is basically powered by federated learning today. But they have these privacy guarantees through DP-FTRL, where they're providing very high privacy values across the board. And that was never, while still preserving almost very good utility. That was never thought of, and they had a 20% drop. They never knew. They thought DPU is not going to work. This is too academic to have any impact. This is private, but not enough utility. But that has been kind of erased. That problem has been erased over the last 5 years or so. So there's still a lot of hope in differential privacy, and so on and so forth. There's been perturbations at different layers of the neural networks, but that's where the most impact has been achieved. Okay, but is this good for federated learning? Not necessarily, because in federated learning, well, it's actually very good for federated learning. Is it good for split learning? Not necessarily, because in federated learning, you're sharing weights of the model. The model that you train, you're sharing the model with the server, which is good. This kind of methods would solve that. But that has some resource efficiency constraints, because there's not enough model parallelism in federated learning, because the whole model needs to be trained by the client, and you can't think of a client to train such huge models. In that scenario, what we had was split learning that came from the collaborative space. So we have a co-design that needs to be done. There's a theme that keeps recurring. Co-design of distributed machine learning methods, or like parallel machine learning methods, with privacy methods. That's where more utility could be unlocked. So what is the problem that needs to be solved for split learning? There, it's very high resource and communication efficiency. That's the privacy for activations, for releasing intermediate layers of your neural network. What are activations? They're just transformations, which is not the entire neural network, but just part of your neural network where your data has been transformed to some extent. Okay, so that's one of our projects that we worked on. We had some good results in there. So in order to explain that, let me just explain formally now. We've seen the word privacy in more of a linguistic way so far. I've been talking about privacy and saying there is some technical proof of privacy in the way of doing privacy. But now I'm introducing a definition, a mathematical definition of privacy. The notion of privacy was called differential privacy. The authors that introduced this won the Turing Award for introducing differential privacy, Cynthia Dwork, and some other authors also won a Gödel Prize. And this is considered a gold standard for privacy. And the definition of privacy has nothing to do with utility. That's some proofs or empirical utility that you can measure later. But this is just the definition of privacy. And what is the definition saying? It's just saying if you have some very sensitive data, D is data, okay? And you have similar kind of data sets, say D and D prime are very similar sensitive data sets. What does similar mean and why do I care? Similar in the sense that, for example, D and D prime have all records the same. Say D has 1 million records about some customers, and D prime has 1,000,001 record. Everything's same, but one additional record. Or everything's same and one less record. So they just differ very similarly. In that setting, what is the worst case attacker you can think about? The worst case attacker is someone who knows everything about your 1,000,000 records, the D. And they just want to figure out what this additional customer's data looks like, which is the worst case attacker. He knows too much information. And they just want to figure out one record from other 1,000,000 records. That's the D prime, right? So how does differential privacy control such an attacker? It's a guarantee on preventing the worst case attacker. Hence, it prevents other attackers too with a better utility. When you apply any algorithm or any processing, it could be as simple as computing a mean or a median, or it could be like as complicated as training a very large neural network. That's the M. When you apply an algorithm, that algorithm is going to be differentially private, meaning satisfying a very high level of privacy. If the probability distribution of the output of your algorithm, when applied on very similar data sets that just differ by a record, or similar in some sense that is very similar, if the probability distribution of the output of your records don't change much, which means you have differential privacy. But what does that mean intuitively? That means that if I apply an algorithm on everyone, on all the 1,000,000 customers, and then I look at the output of their mean, for example, the average salary, for example, and say salary was a protected information. And then I apply the same algorithm, which is just computing a mean, just your plain vanilla average, on all the 1,000,000 plus 1 customers. I look at these two averages. If the average changed by a lot on the higher side, I would know that one customer, I could put a good guess on, actually an exact guess on what is their exact salary. I can reconstruct their exact salary by looking at the averages. I can tell that this person is being paid a lot, and this is their exact number. So that's the PDF, that's the probability distribution that you want to prevent. You don't want that change to happen, which means if your algorithm was magically private, even if you knew everyone's records, your PDFs, your output distributions would not change much. So you cannot reconstruct that record. This prevents identifiability. Hence, this was proven to satisfy the GDPR's clause of identifiability. And that said, it's not magic, right? Because there's always a trade-off in everything. So the trade-off is the epsilon parameter, which is the privacy parameter. And there's an e power epsilon, which is bad because epsilon grows very quickly. E power epsilon grows very quickly. Epsilon is what is, so this is called epsilon differential privacy or differential privacy. Epsilon, when it is low, you have very high privacy because your algorithm's outputs is not changing much. When it is large, it means you don't have good privacy, right? So if you have someone says they have an epsilon of 10,000, e power 10,000 is astronomically large, which means I can figure out that person's salary. Okay, so that's what a definition of differential privacy is. And how is it achieved? It's just a definition. It doesn't tell you how do I get differential privacy. It's a standard that one would like to achieve. And typically it's achieved by introducing some sort of randomization or noise into the pipeline of what you're computing. And then you need to prove that this is the kind of randomization or noise I need to do. Then I have this DP guarantee, which means it's private. But then you also need to make sure that you're not just blindly adding too much noise wherever you want, because you just want to make it private, because you would lose utility. You would get all wrong answers from your machine learning model or your pipeline. So you need to be able to have this fine trade-off between utility and privacy when you design differential private algorithms. Okay, where are we on time? Okay, yeah, it's a 1 hour talk, good. All right, okay, so we've been going at the right pace. So how do you get differential privacy guarantees for neural networks, for AI, when you're sharing activations, because that will let you get very high resource efficiency? That's been our work on power learning, where the use case is follows. Say there's a server with a lot of compute capacity. That could be a company, for example, or a large organization, or some sort of nodal authority that has the capability to train very large models that do very beautiful things. But in order to train such large models, the data that they want to source is kind of siloed all over the place, maybe all across your cell phones, all across all the companies, all across your health records, all across your financial transactions, everything that you'd be scared to share, and you shouldn't be sharing for the safety of yourself. So there's that mismatch. And this is the mismatch that's been happening in this so-called large language model or the foundation model era. Once the GPT was announced, there's been a lot of fines and lawsuits and things about copyright and data because they scrape too much data from the internet. And then there's been a lot of course correction from the companies as well that started accounting for this. And they're going towards like differentially private training of these models and so on and so forth. So how do you enable collaboration in this setting? This is a useful setting that applies to healthcare, to your device, edge device ecosystem, all your smartphones and finance, so on and so forth. How do you enable this? So the way we do it as follows. We have a privatization network, but this is not just a heuristic, because you can always train some new network and say, I'm reducing some notion of leakage of your data and come up with a number, and then say, now my data is transformed or sanitized, and I'm going to release it. That's not enough. That's enough for getting utility. You can always train networks and do heuristic things and hacks and stuff, and also technical stuff, and somehow ensure that you squeeze very high accuracy of your AI model. And this has been progressing very well anyway. That's one of the results of the foundation models is this high utility squeezing capacity of today's machine learners. Of course, is it the most resource efficient? Not necessarily. We are going there. Collaboration will, in a good parallelized way, would enable that. But we need to have some sort of a privacy guarantee on the privatization network. This is standard training, how you would train your utility network, but you need to have a privatization guarantee. For example, if my neural network was just a mirror, literally, it raw data and releases raw data as it is. That's not private. I can call it a privatization network, but that's extreme. I can just add a number to it and say, this is private. That's not private. I can add one layer. I can add 2 layers. I can add maybe 1 billion layers in this neural network. When do I know that it is private and to what aspect? Because we need to meet the guarantee of differential privacy. And then you're happy that it is private to this exact level of epsilon. So for that, what we did is I proposed this new loss function, which you can apply on any neural network or on any composition of functions. For that case, say it doesn't have to be a neural network. It could be any other processing. But neural networks are popular, hence it's also applicable in this setting. It's a new loss function that you apply here that comes with an exact calibration of what is the level of differential privacy that the network would guarantee. How would this work? So what is that loss that will induce privacy into your neural networks? For sharing activations, not for sharing weights, because when you share activations, you have very high resource efficiency. Okay, so there is a fundamental foundational principle, which is called the probability flow, but it's a change of variable theorem is what it's called in the textbooks. But it's a fundamental principle that is a guiding force for this. The principle is as follows. Something out that's the output of your transformations. That would have some distribution of its own because your data has some distribution, your transformations has some distribution. Now, if someone asks the question, if my data was, say, Gaussian to start with, and I apply some transformations, what is the distribution after these specific transformations? If my data was whatever distribution, I don't know its distribution, I just have data, it has some distribution. And I apply some transformations. What is the PDF? What is the probability distribution of the transformations? That's what the change of variable theorem answers. There's an exact formula for that. That answers what is the PDF of the output of your transformations. Why is this useful? This is useful because my definition of differential privacy was a definition based on probability distributions of my output. If my outputs probability distribution don't vary much, then I have differential privacy. So I need to know what is the probability distribution of the output of my neural network, my privatization network. And as you see in this animation, this is the animation I was talking about. This is just a 1D case, but this applies in the real world for all kinds of data. It doesn't have to be Gaussian. This is just for visualization. Say you had some Gaussian data. You applied a transformation, which is just the exponential transformation. And someone asked the question, if I apply exponential, what is the PDF of my Gaussian? Is it still Gaussian? What is it? What is the distribution? That's exactly what the change of variable theorem answers. Any PDF can be transformed, and you can know what is the output of the PDF. So this is useful. That's what you see on the y-axis, which is the other distribution. The same thing holds in 2D and very high dimensions as well. Here I have a grid, which is just uniform data. There's a transformation that is converting into 2D Gaussian data. What you saw previously was a 1D Gaussian, this is a 2D Gaussian. And it's the same formula that answers that. You could plug in anything into your neural network as well, and when neural network does a transformation, you will know the distribution of your output. Now, the way we introduce privacy is based on using the change of variable theorem and doing some work to connect it with the definition of differential privacy, which gives us a specific loss function that we derive. So this is the loss function you plug into your system, into your TensorFlow, PyTorch, your deep learning code. This is literally what goes into the code. You train whatever neural network you want with this loss function instead, and then measure the output of this loss function once you're done training. The output will exactly give you the first term will give you what is the level of differential privacy you achieved. So this is not just math for the sake of abstractness, but this is work that has immediate translation to the problem we had at hand, which is it will tell you any neural network that you give me, what is the privacy level it will or will not give you. It will give you the epsilon value. And there is some calibration so that since it's a worst case guarantee, we make sure the calibration is exact. So, but this is something in pictures that's more easy for you to see the intuition. Say I trained a neural network, and then I passed data through it. And this was really a neural network. And then we looked at the distribution of the data, of the output. This is the level of privacy we were able to guarantee for every single sample. So there's a histogram of privacy levels. As you see, a larger epsilon, a larger x-axis, as I defined, is low privacy. Lower regime is high privacy. So if someone comes up with a question, with a requirement that they want their privacy to be less than very high, which means with an epsilon less than 0.5, then you know which are the samples you can release from your neural network, the output of your neural network. The rest you don't release because you don't satisfy it. But if someone said they wanted something at 2.5, the neural network you have trained is already good enough. You can train all the samples and share all the corresponding activations from your neural network. So there's an exact calibration from neural network to a differential privacy level. And this is more real data too. DP Atom, which is in green, was a de facto way of training neural networks for adding privacy, for releasing the weights of the neural network. But when we pass it through the loss function, we see the epsilon levels were not good enough for the activations. What is happening? Is DP Atom wrong? It's certainly not. Is differential price wrong? It's certainly not. But why are the values large? This is because DP Atom only privatizes the weights of the model. It doesn't privatize activations. There's no guarantee on activations, but the weights of the model are safe. And hence, when you apply this, the activations of this model, although trained on DP Atom, using differentially private Atom or SGD or your optimization methods, are leaking higher loss of privacy. But when we apply our method, this is more suited for activation release, such as in split learning. That's when you see a very high privacy regime. We are able to preserve this very high. Same thing applies on other data sets as well. In terms of other takeaways, because resource efficiency is very important too in collaborative learning, is kind of as important as privacy in some sense. So we achieve a similar or a better utility with our neural networks trained in this way, but the resource efficiency is way higher because the payloads that we're sharing are just activations, not these entire models. For that simple reason, we have a very high communication efficiency. The compute efficiency is also high depending on what is the amount of compute that the client can handle. If it's very less amount, you would offload more compute into the server because split learning allows for that. In federated learning, there's no concept of that. This hugely powerful server is just doing an average of models. Average operation for such a large server, it's not the biggest problem. Training the model is the big problem. So we see comparable or better utilities, but with higher resource efficiencies while preserving privacy. Okay, now some more broader strokes, right? So I shared some more technical and deeper aspects. I shared some earlier aspects about the landscape of privacy and the world we are heading towards and collaborative learning and things like that. These are a bit more broader strokes of where the world is could be heading towards. There's no guarantee on this. I don't have a complete bet on this as well, but it's interesting. So these are the kind of things that are kind of at the edge that could be interesting, may go wild or may not go wild. That's the kind of thing. Right now, it's still a blip in the landscape. It could be a big activity, may not. We don't know. So these are those kind of things. The ones I showed so far are definitely very useful. So those are definitely creating a lot of effort. A lot of it's not just blips, a lot of activity. So here. We've been, like I said, we've been talking about Amazon for markets for tangible goods, but we're we are guessing that there would be markets for data and models. And when I say a market, there would be an exchange of value in the value chain proposition and exchange of money as well. But data is very different. It's not a tangible good. It's not like an apple that I buy at the market and then return it because it's nothing good. It's not like a laptop that I buy and return it because it's not working or it's not up to my specs. Data, once you buy it or once you sell it, it can be replicated again and again. There's no guarantee of return, right? Unless there's some verifiable guarantee that the data can never be looked at, but can be used, but returned, things like that, unless there's a privacy enhancing tech on top of that. And data is replicable. There's always machine learning, but there's a question of machine unlearning. If I tell a company to remove my data and unlearn everything that they've done, it's a hard problem. Unless there was a tech for it. Because if they just removed a record, one person's record to satisfy compliance, because they don't want a lawsuit on the company, because the person has a right to delete in some of these laws that are coming up. When he poses a right to delete, the company, in the naivest case, can remove the data of one record and retrain the model on billions of records except one record. That's a lot of work. Of course, that's not the naivest solution that the company would use. There's a lot of smart people in the world that are trying to solve this unlearning problem. There are some better solutions to this. Every problem of this sort has a lot of activity that is potential in this area. So we came up with this work that's kind of available online with Michael Jordan and Ramesh and so on and so forth. That solves this problem of data acquisition. How would you know for the task that you have at hand? A buyer is requesting data. The data buyer has a task at hand. And by a task, he has data and some labels for a validation set. But he needs more data. That data is not enough. They just have a way to gauge how good the data that they've acquired, but they need more data so that they can continue to gauge. But these labels are sensitive data, right? So the buyer cannot share all its data just because it wants to acquire more data, right? You can't think of company selling its data because it wants to buy more data. That's not how it works. The company has its own sensitive, trademark protected, copyright protected, sensitive, privacy compliant data. So, and the labels are sensitive too. So our method, think of healthcare. This is the setting we're using to show the diagram, right? The disease status, which is what the models try to predict or improve, itself is a very sensitive record, right? Just your label, the thing that you're trying to predict. And that's also sensitive according to HIPAA compliance, right? Which is a very stringent healthcare law for privacy, for healthcare data. So without sharing labels, we share a method where the buyer could identify from an auction of sellers, of data sellers, of which is the specific records from each seller that it needs to acquire, so that in the task that it cares for which it is not sharing the labels, there would be an improvement, the most improvement in its performance. Because you can't just acquire data by the bulk, right? Because if someone is paying, say, even $1 per record, and if you acquire by bulk, it could very likely be possible in the cartoonish scenario that I could create 1 trillion records that are almost the same, that are not going to add a value worth $1 trillion. It's just you're spending $1 trillion for $1's worth of value, because in the end, all the trillion records are almost worth the same record, which is $1 value, right? So this is a data market. So when you do things like federated learning or split learning or collaborative machine learning, there is payment that needs to go to the right people who are engaging as clients in this collaborative learning framework by allowing their sensitive data to be tapped into by the server in some privacy-preserving manner so that the server has a very powerful model, right? So the raw material to product. And you need to figure out which person gets reimbursed by what amount for their data. And it cannot be done in bulk, so it needs to be a structured way to do it. So you need to have some guarantee of improvement. So our method allows for such data acquisition capability. Okay, so we've seen these problems. There's another real world problem that's happening in today's world, which is the problem of inference, which is predictive inference, or like just predicting from a model, right? Because if you're training a model with privacy and your sensitive data that you're acquiring to, say, train a foundation model or a little model, doesn't matter, is privacy with respect to training data. This is an important concept. The unit for which you're giving privacy is the training data. There is no guarantee for privacy when you deploy the model for the test data on which you want to get the predictions from, because now you have a good model, maybe learned through collaborative learning. There's no predictions. There's no price for prediction. And where does this happen? This happens everywhere. It also happens in our rooms when there are smart devices, for example. you are saying whatever you want to say to your smart device. There is no guarantee that the transformation that is going from your smart device to the large server holding company, right? That your speech is protected. There's no guarantee there. Of course, there are laws that are forcing the companies to provide these guarantees, but these guarantees need to be provided in a technical way, like adding differential privacy or something of that sort. But differential privacy for inference, although inference is such an important problem, because all of ChatGPT is an inference problem, right? Because after training, of course, there's a training privacy problem. After training, all of us are just using ChatGPT as API users to ChatGPT. You just go to the browser and use it as a service. That's just an inference problem. And I can say whatever I want in the prompt. And maybe I'm a company that is holding very important legal data, or I'm a company that's holding very important healthcare data, or even precious genomic data. I can just share it into the prompt and ask ChatGPT to do something because it's smart or so-called smart. I'm losing my inference, my privacy during the inference stage. This is an important problem. And there's been a very important reason why this problem, although important, doesn't have enough solutions. So it's a hot cake kind of problem. It's a good area to work in. It doesn't have solutions because when you do something like differential privacy, you could say infinite possible things. You would have infinite possible outputs. Your statistic is a one-to-one map. Unlike in training, you can use infinite records or like billions of records, but you have only one input, one output, which is a statistic. Your machine learning weights are a statistic learned or estimated through gradient descent. So when you have a one-to-one problem, people have proved that there's an impossibility theorem, which means there's a problem that's impossible to solve. So if someone is selling that they're solving this problem, they're selling snake oil if they're promising differential privacy. That's not doable. But there's getaways around it. There are relaxations to it, which will get away around this impossibility. Hence, this was not the first thing that the smart people started thinking about. They first thought, let's first solve releasing statistics with privacy. Let's do some analytics. Let's do some hypothesis tests with privacy, which people are still working on. Let's do machine learning training with privacy, for which there's been good progress in the last 10 years, very good progress. But now this is where people will start getting towards, because foundation models is all about inference. Okay, so we have some solutions that we published in NeurIPS for the inference problem. And I will encourage you to look at it and feel free to reach out to me. And as I have a couple of closing slides. So however important collaborative machine learning is about different kinds of parallelism during training for resource efficiency, equally important is also the problem of private machine learning or privacy preserving, or like machine learning that is compliance to all kinds of laws, not necessarily privacy, even other laws. And there's a big room for a co-design of the distributed machine learning methods or like distributed data science methods and privacy preserving or trustworthy or responsible data science methods. When I say responsible or trustworthy, you can replace privacy with other problems because there are other problems that also require compliance for technology companies. And there's from academically as well, there's a whole lot of open problems in open space at the intersection of privacy and well-established areas. So there's some interesting problems. There's a good mapping of these problems to work on, and so on and so forth. I kind of conclude here. And if there are any questions, I'm happy to take as well. And then there's the networking I'm looking forward to.
Thank you so much, Doctor, for the insightful presentation. So we will open it for questions here for our in-person attendees. And then we will take one question from the online attendees as well. Thank you.
Thank you so much, Doctor, for the informative presentation and for allowing us to attend today. This is Abdulrahman Simri speaking. I would like to ask regarding for the transformation. Is it going to be applied for the data or for the distribution itself as, let's say, part of something like truncated distribution or something similar?
Yeah, it would. Okay, the simplest case is to apply to the data and ask the question. If the data had some distribution, you apply some transformation, what is the distribution after the transformation? That's a simpler case, but that doesn't mean that it's not applicable to transformations on top of transformations, which is actually kind of the building block in the method that we proposed on power learning, which is you have compositions of functions. Neural networks are transformations of transformations. And there are two kinds of neural network modeling, right, broadly. One that is probabilistic, things like diffusion models and things like that. They are kind of learning distributions at different layers of the network. At the same time, there are some that are more brute force, just optimizing for the weights. So it's kind of the founding principle is kind of applicable to any f of g of x, and you can choose whatever f and whatever g, and f itself could be like 10 transformations, and g could be 5 transformations, doesn't matter. Yeah. Sure, yeah.
Yeah, if that transformation is going to happen for, let's say, the input data, is it should be happen for the data that's going to be used for predictions? I mean, after the training the model for in the prediction phase, and that's going to be record by record, or should it be, let's say, collectively with all the data if it's multi-layers decomposition or multi-layers transformation?
No, I'm very happy you asked. I'm kind of thankful for you asked this finer question. It's a very valid question, and that's where applicability of this method comes in different cases. So basically, it's for you have a bunch of questions. So one of the question was about whether transformation is applied record by record once you have the transformation figured out so that it is inducing privacy, right? So it is record by record during training or during inference. You apply the transformations. First, you learn the transformations that guarantee privacy. You first learn the transformations that guarantee a formally guaranteed amount of privacy. And then you can start passing records through it. And before you release the output of your transformation, all that is guaranteeing privacy, you can still verify the histograms that we're generating, right? Like what is the specific level of epsilon, the privacy level that I give for any activation. And then you use that for training as a batch, or during inference, it is one sample anyway, things like that. Yeah, cool.
We have one question from the online audience. The question is, how do you consider latency under a decentralized approach where high throughput and real-time information exchange is critical?
This is an ongoing problem. This is one of the, well, this seems like a general question about how do I consider latency, but I would just like to state that this is an ongoing problem that people are trying to push the limits for. Especially, let me be more realistic of what's happening. Usually a company never has one model, right? Or an organization has a slew of models being applied at different parts of interactions during their products and services that the company or the organization is providing with using the data, the sensitive data, right? So when there is a slew of models, a company literally has a zoo of models. In the systems area of machine learning, people call it a model zoo, right? And once there's a model zoo, there's a load balancing problem that shows up, both for training and maintaining, and also the privacy, and also for during inference. And for latency, even for simple tasks such as inference, because latency during training is a problem anyway, but inference is where the customer is impacted the most. Because say I type something into ChatGPT and I get the answer 6 days later. That's very high latency. It's just an inference task. But they have a lot of models, and there's a model zoo component. So as people are always trying to find some sort of a Pareto or like some sort of an efficient trade-off, just like you have efficient frontiers in finance, they're trying to find a good trade-off between latency and utility when they have like 100 models that they can use. So this is a problem, that's a real trade-off people are trying to push, and there have been different solutions. And of course, no solution is a silver bullet, but most in real world are like that. There's always some room for improvement.
Thank you so much, Doctor. Thank you so much for the great presentation. And I would like to thank everyone who attended today. And a special thank to ADGM Academy for their endless support and for hosting Adia Lab seminar today. And this marks the end of today's seminar. Thank you.
Thank you so much for organizing. Thank you. Amazing.